All right, so I wanted to go through these Unit 1 review slides. This is slides 5 through 10, and I'm just going to go ahead and solve them and explain as I'm going. Please take your time and follow along with me. You can skip ahead to any slide that you're on. So if you're not on slide 5 right now, you're on slide 7 and you want to check that answer, go ahead and fast forward. But let's talk about how we would do each of these problems. So first of all, this says match the correct sequence, recursive definition, explicit definition, and the rule. So each group should have 4 things in it: a sequence, a recursive definition, an explicit, and a rule. So first thing I'm going to do is just get myself organized. So I found a sequence right here, just a list of numbers, and I'm going to start grouping them. I know that these don't go together, but I just can't see everything right now. So I'm going to try and get myself situated. Start grouping, grouping rules together. So anything that's labeled as a rule, I'm going to group that. And I'm just going to hide them for a second so I can finish grouping at another rule. Let's see now, and another sequence. Okay, so I found all of those. And now I got a bunch of definitions, either functions that are recursive or functions that are explicit. So how can I tell the difference? Very, very easy. An explicit definition does not have the symbol f of n minus 1 in it, and it also doesn't tell you f of 1. So this one is just the function, and that's it. So anything that just has a function by itself is a explicit function. This one, do you see how it says f of 1 equals 5, and it has an f of n minus 1? That is recursive. If you don't remember what those two words mean, you're just going to want to go ahead and look those up online. And I'm just going to sort these as explicit and recursive. So let's see, there's another recursive. It's got f of 1. And these ones don't. Oh, this one does. There we go. Oops, I think I got a mistake in there then. Let me double check it. It was just that last one. There we go. Now that I got all my groups kind of situated, I'm going to hide these ones. And I'm going to try and match my sequences to their rules. So let's pull the sequences out so we can see them all. And let's go ahead and figure out what rule goes with which sequence. So here are my rules. So add 3 to the previous term. So which of these sets of numbers just shows adding 3 each time? So this one's plus, if it was adding, it'd be plus 10, but then it doesn't work for this next one. So that one's not plus 3. This one looks like subtraction down here. This one is add 5 to start, so that wouldn't work. This one's also add 5, so that doesn't work. So it must be this one. Look, let's look at it. Add 3 gives me 5, plus 3 more is 8, plus 3 more is 11, plus 3 more is 14. So that's the correct rule for that one. So I got that one started. Now what? Multiply the previous term by 3. So which of these shows multiplying by 3? And it was this one. Let me group those together. Times 3 is 15, times 3 is 45, times 3 is 135. Subtract 2 from the previous term. The only one that was subtraction was this one, and it is subtracting 2 every time. Minus 2, minus 2, minus 2, minus 2. And then we have adding 5 or multiplying by 2. So of these two, it looks like this one is adding 5 and this one is multiplying by 2. All right, so I got a good start going. I have the sequence and the rules matched together. Now I'm going to go ahead and start pulling out some of my definitions. So I want to start with recursive. I think that one's easier. So let's read our recursive definitions and see what they say. So this one says start, f of 1 means where do you start? You start at 3. So which of our sequences start at 3? Just these two right here. 3, 1, negative 1, negative 3, negative 5, and 3, 8, 13, 18, 23, 28. So I already know that this first one goes to one of these two. That one starts at 5, this one starts at 2, this one starts at 5. So now I got to look at the rule. What does the rule say? Take your last number and add 5. Well, that's easy. This one's the one that says add 5 to it. Do you see how it says add 5 and there's a plus 5 in my equation? Done. Next one, start at 5 and then multiply by 2 every time. That's what this says. Start at 5 and then you see this times 2, it means multiply by 2 every time. Got that one. Start at 2. So there's only one that starts at 2, so I'm already done with that one. Got it. And then we have this one starts at 3 and this one starts at 5. So that makes it easy. 5 goes with 5, 3 goes with 3, and I've sorted those ones now. So now let's see if we can find our explicit definitions. So let's pull up a few of these. All right, so how do I find the explicit definition? Well, it's very similar. Basically, if the rule is multiplying, then it is a exponential function like this one. So 5 times 2 raised to the power of n minus 1. So these two are both multiplying rules, and the rest of these are addition rules. So let's just hide everything that's addition for a second. So this one says multiply, this one says add, I'll hide that one. Multiply, subtract, hide that one. So my two exponential functions go with my two multiplying rules. They both start at 5. Let me highlight this actually. They both start at 5. And look at how that shows up in our exponential function. Our starting place is, remember, we start at a times b to the x. That's what our exponential functions look like. So our starting place is 5 on both of these. The difference is the base. So the base here is a 2, and the base on this equation is a 3. So how does that relate? Well, that relates by our rule. Multiply by 3 or multiply by 2. So now it's pretty easy to tell which one is which. Let's go ahead and group them. So let me clear my drawings and let's group. Multiply by 2 goes with 2. Multiply by 3 goes with 3. So those two are done. They have matched all 4 cards. Now I got a few left. These are my addition ones. And these should be pretty quick and easy as well. So let's look at all 3 of our explicit definitions for addition. So on this one, the rule was subtract 2, and we started at 3. So let's see how that shows up in our function. Our slope, we're subtracting 2 every time. So we move over 1, we go down 2. We move over 1, we go down 2, right? So that represents slope. We're subtracting 2 every time we go to the next term. Go over 1, we go down 2. We go over 1, we go down 2. So there's our slope right there. Let's look at our linear equation. And look, this is in the form of y equals mx plus b, where our x is what we're plugging in. We're plugging in values for n. Our m is our slope, which is we're going down by 2 every time. And our starting place, our intercept is b, which that is where we started. So right there, we see a linear equation, pretty easy. We're just going to match those two together. Goes together. So this one has a slope of 3 and it starts at 2. So this one has a slope of 3 and starts at 2. We're adding 3 every time and we started at 2. This one has a slope of 5 and we started at 3. Started at 3 and we're adding 5 every time. And there you go. We have just found all of our card matches. Okay, let's get moving on. So looking at this next one, we have a function. Here's a graph of the sequence R. And so it says define R recursively using function notation. So we have 3 student samples, student A, B, and C. And so we want to know which student's response is most correct when defining R recursively using function notation. So let's take a look at what we have here. So the first thing we want to know is, so this is a 1 and this is a 3 on our graph. So what are the coordinates of this function? When you plug in 1, it looks like if this is 5, 4, 3, 2, 1, this is the point 1, 1. This one is the point 2 comma, and it looks like 2. This one's 3 comma 4. This one's higher, so it's 4 comma, and it looks like it's 8. Just finding the coordinates. And then this one is 5 comma 16. Okay, so I found the coordinates. So what should my function do? Well, it should go, my first number in the sequence is a 1, then it's a 2, then it's a 4, then it's a 8, then it's a 16. So what is the rule with this? I can see that I'm just multiplying by 2 every time. So I know that I am multiplying by 2 times the previous term. Okay, so let's go ahead and look at these. Based on the graph, the sequence is 1, 2, 4, 8, 16. Yep, that's what I got. So this checks off so far. So the recursive definition is R of n, our function, is equal to R of n minus 1. What does this represent? That represents the previous term. If I want to know R of, let's say 5, which is equal to 16, it's the 5th slot, 1, 2, 3, 4, 5, right? It's my x coordinate. If I want to know what's in the 5th spot, I can just take my 4th spot and multiply it by 2. 8 times 2, right, will give me 16. So this definition says take the previous one and multiply it by 2. That looks pretty good. Let's keep going though. Same sequence for student B. Now they have R of n is equal to R of n times 2. Well, this one doesn't have the minus 1 on it. So what this one says is if you want to know what's in the 5th slot, take your answer for the 5th slot and multiply it by 2, and that'll give you the previous value. So if I multiply 16 by 2, it comes back to 16. That doesn't make sense. 16 times 2 would be 32, which would be what is in the 6th spot. So that one did not work. So this is no good because it should have had an R minus 1 right there. All right, let's look at the last one. Based off of the graph, the sequence is 1, 2, 4, 8, 16. That's the same. Oh, but look at this. They told us where to start. R of 1 equals 1. And they told us the rule. Multiply the previous term by 2. The previous term is being multiplied by that 2 right there. And they said that this works for anything bigger than 2. So after I know that R of 1 is 1, now that I know this one, I can start the rule. It works. So I can look at the previous one and I can double it. It'll give me the next one. Look at this one and double it. It'll give me the next one. Look at this one, double it. It gives me the next one, right? So now I see that it starts on the right place. It has the right domain and it has the right rule. So which student was correct? Most correct? Well, student A had a very good answer, but they forgot where to start. So C is the better answer. Student C correctly identified the starting term, and then I'll actually write it. R of 1 equals 1. And the function R of n correctly shows that we are multiplying the previous term by 2 for any n greater than or equal to 2. Okay, so that is why student C is correct. And let's say why the other two are incorrect. Student A is incorrect. Oops. because they forgot the starting term. And student B is incorrect because they did not use the previous term in their function. And I'll make a note that the previous term was supposed to be f of n minus 1. So I'll just make that clear. That's what they should have had in their function. Okay. All right, let's keep going. So an arithmetic sequence starts at 84, then 77, and so on. Define it recursively. So what did they tell me? They told me a few things. Number one, it's arithmetic, so I know I'm adding or subtracting. So what would I subtract in order to get from 84 to 77? I would need to subtract 7. So the rule is subtract 7 each time. Define the function a recursively. So I need to have the starting place. So f of 1 equals 84. This one has it. Student A did a good job there. Student B again left it off. Oh, they forgot the starting term. So nope, that's not good. And this one says a of 1 equals 84. So both of them have the starting term. That's a good start for A and C. Now, which one correctly shows the that we're subtracting 7 from the previous term? So A shows the previous term right here, and they show the subtracting 7. C shows the previous term, and they show the subtracting 7, but they also include the domain. So right now for A, I might not know if can I plug in n equals -7? Right now, without a domain, I can plug in any number in, but that doesn't make sense for a sequence. Sequences start at 1 and they count from there, right? This is my first term, my second term, my third term. I don't have a -7th term when I'm looking at a sequence. So student A doesn't make sense. Another thing that student C did that I liked is it said the problem says define A recursively. And these two students define functions called f. But student C defined their function also matching what the problem said, calling it function A. So they did it most correctly. Okay. So again, what did they do correctly? I'm not going to write it out. You can just check your work with me, but they correctly identified the starting term. They correctly identified the rule of subtracting 7 each time, and they had the right domain. A and B, A left off the domain, and they forgot to define the function A instead of defining it as f of something. Student B forgot the starting term, they forgot the domain, and they forgot to use A instead of F. Okay, so C is the best answer. All right, let's keep going. A geometric sequence, G of n starts at 20, then 60. Define G recursively. Okay, so I need 3 things. So I need my starting term. I need my function. And I need my domain. Those are my 3 things that I need in order to correctly define this recursively. All right, so what's my starting term? Well, I start at G of 1 is equal to, so what's my first term is 20. Okay, off to a good start. What's my function? Well, it's geometric, means multiplication. So 20 times what equals 60? The rule is going to be multiply by 3 every time because it's geometric. So I'm going to multiply 20 times 3 to get to 60. So let's go ahead and write that function. G of n is equal to your previous term, G of n minus 1 times 3. That's it. And then what is my domain? Well, my domain is always one bigger than my starting spot. So if I start at 1, my domain can be anything bigger than or equal to 1, or anything bigger than 1. So anything greater than or equal to 2. So if this is a 1, this is a 2. If this is a 2, this is a 3, right? It's always one bigger. Cool. All right, so that is my recursive function. Now, what about if I want to define g of n for the nth term? So this is an explicit definition. So for this one, I only need the function and the domain. I don't need the starting spot, okay? Because the starting place is going to be in the function. We'll see in just a minute. So geometric means that it is a exponential function. So my function should look like a times b to the x power. So what is my starting position? Well, it was 20. And what am I multiplying by every time? I'm multiplying by 3. 3 is my growth factor. And I'm going to raise that to, I need to find my exponent. So when I plug in, let's just think real quick. When I plug in a 1, I should get 20, right? So what would my exponent need to be when I plug in 1? I want it to equal 0 because 20 times 3 to the 0 equals 20. So I need n minus 1. This function, when I plug in a 1 right here, that'll give me 20 times 3 to the 0 power. When I plug in a 2, that'll give me 20 times 3 to the first power, which is 60. So I want that as my function. And now my domain is going to work for any number I want to plug in. So any number bigger than 1, because I can plug in a 1 here and it still works. Oops, that's supposed to say domain. There we go. All right, so there's my explicit exponential function for that geometric sequence. 20 times 3 raised to the n minus 1, and it works for n bigger than or equal to 1. All right, final one. Now I have an arithmetic sequence. It starts at a of 1 equals 4, and then it goes to a of 2 equals 16. So how would I find the value of a of 15? Okay, so my arithmetic sequence means that I'm adding every single time. So my function, if I start at 4, and then my rule is I want to add 15 every time. So a of n is going to equal a of n minus 1 plus 15 every time. And it's going to work for n greater than or equal to 2. So my pattern works. I just wrote my recursive definition. Now, one of the things I could do is I could just do this 15 times. So I could say, okay, I got 4. And then when I add 15 to that, oh, it shouldn't have been 15. Sorry about that. 4 plus what is 16. So that should be 12. There we go. 12 is the right one. So I go 12, then 16. And then if I keep following this pattern of adding 12 every time, I can get there. So next one's 28. If I add 12 again, I'm at 40, right? And I can continue this pattern. But it's going to take me a while. I got to do this 15 times. I've only done it 4 times. I'm already tired of it. So instead, I'm going to write an explicit definition. So the definition of this one is going to be a of n is equal to, what am I adding every time? So my slope of my function is going to be to add 12 every time to the term I'm on. And then I want to start at 4. So there is my linear equation, a slope of 12, a starting place of 4. Okay. So now I can plug in any number I want into this, and I will get the answer. So I'm going to plug in 15 here. And this will give me the correct number. So 12 times 15 minus 1 is 14 plus 4. So that is 12 times 14. Let's do it real quick. 12 times 12 is 24 or 124. Let me pull it up. So it's 168 plus 4, which gives me 172. So this is much easier using the explicit definition than trying to go through all these steps to eventually get to 172 on the 15th step, right? That'll take me way too long. All right. A geometric sequence is g of 0 equals 4 and g of 1 equals 16. Explain or show how to find the value of g of 15. So we're not going to make this mistake of doing a recursive definition again because it takes too long. Let's find our function for the explicit. So we want to know what g of n is equal to. It starts at 4. And what are we multiplying by every time? So it looks like 4 times 4 is 16. So I must be multiplying by 4 each time. And it's to the n minus 1, because that is the term that I'm on. Okay, so I have 4 times 4 raised to the n minus 1. Now that I know that, I can plug it in. I can plug 15 in. So I'm going to plug a 15 in right here and right here. So what will I get? I get 4 times 4 raised to the 14th power, which 4 to the 14th, ooh, that looks like something that's going to be really, really big. Let's try it in the calculator. 4 to the 14th power. Oh yeah, that's huge. So we get 435,456. Very big. And I have that 4 out front, so I want to multiply it. That gives me my value of g of 15 after I do all the calculations together is equal to 1,073,741,824. So that's how I would calculate g of 15. All right, that's the review for Unit 1. Good luck to you on the final, and we will see you in class.